The basicity constant, Kb, is your measure of the strength of a base in an aqueous solution for the following chemical reaction. A weak base, B, plus water, exists in equilibrium with its conjugate acid, BH+, plus hydroxide. Or equivalently, we can write the reaction as shown here. The weak base A- plus water exists in equilibrium with its conjugate acid HA plus hydroxide. In both cases, we can define an equilibrium constant for those reactions. And just like with all equilibrium constants, our equilibrium constant Kb is defined as the concentrations of the products, the concentration of BH plus and the concentration of O minus in this case, divided by the concentrations of the reactants, which is the concentration of B in this case. You'll notice that water is not included in the equilibrium constant expression because it is a pure solvent. For the reaction shown here, we can also define an equilibrium constant Kb, which is the concentration of the products, HA times hydroxide, divided by the concentration of the reactants, A minus. So, just like with pKa's, we can define a pKb for our bases, where pKb is defined as the negative logarithm of the Kb. So just remember that the term p just means to take the negative log of the value. And similarly, if we know the pKb, we can calculate the Kb using this expression, where Kb equals 10 to the power of negative pKb, or the inverse log. Kb is called the basicity constant, or base dissociation constant, as we mentioned previously, and it's a measure of the strength of the base. So the stronger the base, the higher the degree of dissociation of the base, and the larger the Kb value. For a weak base, we have a lower dissociation of the base and a smaller Kb value. Here we have a table of pK values for some common weak bases, as shown here. Now, even though these are all weak bases, the convention in chemistry is that we typically cite the pKa value for the conjugate acid of the weak base that we're interested in. So here in this table, the K values are actually the pKa values for the conjugate acids. This is particularly true for organic chemistry, where all weak bases are represented by their pKa values. The strength of the bases increases as we go down the table, so increasing pKa value represents a stronger weak base. In this slide, we'll look at the relationship between Ka and Kb for a conjugate acid-base pair. In this example, we happen to be looking at the weak base reaction for ammonia and the weak acid reaction for the ammonium ion. However, the discussion applies to any weak acid, weak base reaction. So the weak base reaction for ammonia has an associated Kb, or base dissociation constant, related to it, and the weak acid reaction, which is also shown here, has the following Ka equilibrium constant associated with it. Multiplying those two together gives us Ka times Kb, which equals the expression for Ka, which is the concentration of H3O plus times the concentration of ammonia, divided by the concentration of the reactants, which is the ammonium ion. And for Kb, we have the concentration of NH4 plus times the concentration of OH minus divided by the concentration of the ammonia. And as you'll see from this expression, as it happens, the ammonias cancel and the ammonium ions also cancel, leaving us with Ka times Kb equals the concentration of H3O plus times the concentration of OH minus. Now we've seen this before, and that product just equals Kw, the equilibrium constant for water. So what this tells us is Ka times Kb equals 1.0 times 10 to the minus 14 at 25 degrees Celsius, which is the value for Kw. So this relationship is important because it tells us that if we know Ka, we can automatically calculate Kb and vice versa. So knowing one, we can automatically calculate the value of the other. Going one step further, if we take the negative log of both sides of this equation, we get negative log of Ka times Kb equals a negative log of 1.0 times 10 to the minus 14. Expanding the brackets gives us negative log of Ka plus the negative log of Kb equals 14.00. You'll notice that 1.0 times 10 to the negative 14, which is the Kw value for water, has 2 sig figs, and once we take the log of that, we have 2 decimal places, which is the same as 2 sig figs for logarithm values. Now, the last step here is to recognize that the negative log of Ka is just what we call the pKa, and the negative log of Kb is what we call the pKb. This leads us to the relationship pKa plus pKb equals 14.00. And again, this is significant because it tells us that if we know one, we can automatically calculate the other value. Right? So these two equations led us to calculate any one of the 4 parameters using just one of the parameters. Putting everything together gives us the pK box, which basically shows us how to calculate all the other properties of the system knowing just one of the values. So for example, if we were given the Ka value, we could easily calculate the Kb value using this expression, Kb equals Kw divided by Ka. If, however, we wanted to calculate the pKb from the pKa, even though there are 2 equivalent roots, either this way or this way, it's actually slightly easier to calculate the pKa first. So from the Ka, we would calculate the pKa using this expression, pKa equals a negative log of the Ka, and then calculate the pKb using pKb equals 14 minus the pKa. So the reason why this route is a little bit easier is that this final step is a subtraction instead of a multiplication or division, as we would have in the first step here. In this example, we are asked to calculate the concentration of H3O plus and the pH for an aqueous solution of ethylamine, which is a weak base that is a precursor to the production of many herbicides, such as atrazine and simazine. In this question, we are given the concentration of the weak base, so this is the initial concentration of ethylamine, as well as Kb, the base dissociation constant. And we're asked to calculate the concentration of H3O plus and the pH. So the strategy for this question is first to write the balanced chemical reaction for this acid-base reaction. Next, to write the ice table, initial change in equilibrium concentrations, and then to calculate the concentrations of the species of interest. The first step to solving this problem is to write the balanced chemical reaction. Starting with ethyl ammonia, C2H5 NH2, plus water, which exists in equilibrium with its conjugate acid, ethyl ammonium, C2H5 NH3+, plus hydroxide. So this is the balanced chemical reaction. As you can see, the atoms are balanced, but the charges are also balanced. On the left, we have a charge of 0, and on the right, we have a charge of +1, -1, which also equals 0. Next, we want to complete the ice table. So we want to write the initial, change, and equilibrium concentrations for each of the species in this reaction. The initial concentration of ethyl ammonia is 0.085 molar, which was given in the original question. For water, we should recognize that water is a pure solvent, and for pure solvents and pure solids, we don't write the concentrations, we just put a line through that species. Next, for ethyl ammonium, we have the initial concentration of 0, because we don't have any ethyl ammonium in the question to start with. Similarly, for hydroxide, the initial concentration for hydroxide is also 0. Next, to get the change in the concentration for each of these species, we have to recognize that because this is an equilibrium reaction, we actually don't know how far to the right our equilibrium lies. And since we don't know how far to the right, we write a change in concentration equals x. Negative x for the reactants and plus x for the products. So for ethyl ammonia, the change in concentration here is going to be -x. Again, since water is a pure solvent, we just put a line through that species. For ethyl ammonium, we have a change in concentration of +x, because this is a product. Similarly, for hydroxide, the change in concentration is also +x. Next, for the equilibrium concentrations, we simply add up the columns. So 0.085 minus x gives us an equilibrium concentration of 0.085 minus x. Since this is water, again, a pure solvent, we just put a line through it. And for ethyl ammonium, we have 0 plus X, which gives us an equilibrium concentration of X. Similarly, for hydroxide, it also has an equilibrium concentration of X. Now, this last line in our ICE table is very important for us because it will help us to calculate the equilibrium concentrations of each of the species that we were interested in. The next step to solving this problem is to write the expression for the equilibrium constant. In this case, we have K, which is our equilibrium constant, equals the concentrations of the products divided by the concentrations of the reactants. You'll see here that the concentration of H2O is not included in our equilibrium constant expression because water is a pure solvent, and pure solvents are not included in the equilibrium constant expression. Also, this equilibrium constant is a special equilibrium constant in that it is the equilibrium constant for a weak base reaction, as shown here. And so this is given a special notation, Kb, base dissociation constant or basicity constants. Next, we just substitute the values in for each of these terms in our equilibrium constant expression. So Kb has a value of 4.3 times 10 to the minus 4, which was given in the original question. The equilibrium concentration of ethyl ammonium is X, so we write X here, and the equilibrium concentration of hydroxide is also X, divided by the equilibrium concentration of ethyl ammonia, which is 0.085 minus X. So we see here that now we simply have to solve for X. That's essentially the mathematical part of this problem. As we'll see shortly, the equation on the previous page essentially reduces to a quadratic equation. Now, some people don't like solving quadratic equations. So in some cases, we can use an approximation to simplify that quadratic equation. But before we can use the approximation, we have to test whether or not that approximation is valid. And there's a very simple test for that, namely, the initial concentration of base divided by Kb, the base dissociation constant, has to be greater than or equal to 400. So substituting the values in for the initial concentration of base, we have 0.085 divided by Kb, which is 4.3 times 10 to the minus 4. And plugging this into our calculator gives us a value of 198. So unfortunately, in this case, because the initial concentration of base divided by Kb is less than 400, we cannot use the approximation, and we have to use the quadratic formula. So rearranging the equation that we saw on the previous page gives us x squared plus 4.3 times 10 to the negative 4x minus 3.655 times 10 to the negative 5 equals 0. So we can clearly see that this is indeed a quadratic equation. So in order to solve x for a quadratic equation, we use the quadratic formula, which is x equals negative b plus minus the square root of b squared minus 4ac divided by 2a. Now you'll see that this plus and minus sign would indicate that we should have two roots for our quadratic equation. However, one of these roots we can see will be negative, and it is impossible to have a negative concentration. So we can shorten this calculation down a little bit by only taking the positive root. So solving for x with a positive root gives us a value of 5.8 times 10 to the negative 3. Now, this is the value for x. But the most important question that we have to ask ourselves is, what is x? So from the ICE table, we would remember that x is the concentration of hydroxide, which is therefore 5.83 times 10 to the minus 3 molar. Knowing the concentration of hydroxide now, we can calculate the pOH for the system using the formula pOH equals negative log of the hydroxide concentration. And substituting the value in for hydroxide gives us pOH equals negative log of 5.83 times 10 to the negative 3, and this gives us a value of 2.233 for the pOH. You'll notice that our hydroxide concentration has two significant figures, and our pOH has two decimal places, which represents two significant figures because this is a log value. Next, we can calculate the concentration of, or we can calculate the pH using the equation the pH equals 14 minus the pOH, and this gives us 14 minus 2.233, which gives us a pH value of 11.766, and the H3O plus concentration can then be calculated from the pH using this formula where the hydronium equals 10 to the power of negative pH. Substituting this in gives us an H3O plus concentration of 1.7 times 10 to the negative 12. Final answer, 1.7 times 10 to the negative 12 moles per liter as the concentration of H3O plus.